All right, we are back, so let's get back into the swing of things. So, to recap, we introduced this model called a linear bounded automaton, and we were able to show that A sub LBA was in fact decidable. So there is a stark contrast between what an LBA could recognize versus an actual Turing machine. Yeah, go ahead.
But it's limited as to like the languages it can understand, right? 'Cause it's
Yeah, by definition.
Okay.
Yeah. There must be some language that a normal Turing machine can recognize, but an LBA can't.
Like and one of like the one on the test, for example, that we just had. That one you can't shift over all of your input one, right?
Yeah. So a LBA can't shift over the input, but that doesn't necessarily mean that it can't recognize the language in some other way. Okay. Yeah. So it certainly can't shift input. You're correct. Okay. Mm-hmm. Other questions? Okay. So when we talked about A sub whatever, DFA, CFG, Turing machine, or whatever, the next one we talked about was emptiness for that particular model. So let's talk about E sub LBA. So M is an LBA and has empty language. So, like before, we showed that E sub CFG, or PDA if you like, was decidable, and we showed that E sub TM was undecidable. So again, here we don't necessarily know what is decidable versus not decidable here. But we'll in fact show that this is undecidable. So the problem of asking whether an arbitrary LBA has empty language or not is undecidable. Okay, well, so we're going to take a little bit of a detour back into computation histories that we defined earlier. So if we go back, where we talked about these configurations, it's just the sequence of configurations that the machine was on, and each one yields the next one using a valid transition. Okay? So the way we write a computation history, let's say C0, C1, up to Cm, by putting a delimiter in between each one. Okay? So let's ask this question. Given a Turing machine M and W, can an LBA figure out whether this computation history is accepting? So remember, an LBA can't use more tape than what was given on the input. So we're given this # delimited sequence of configurations.
So then it would have to be less than, the computation M has to be less than Q to N.
No, all I'm doing is recognizing whether this string is a valid computation history or not. Well, what do I need to check? Let's say about C0. What has to be true of C0? Yeah, it has to have the start state and the input W exactly as is. Okay? It must be the start configuration. Otherwise, could it be a valid computation history? No, it can't be a valid computation history. So the first thing we need to check is check if C0 is a valid start config. Which, given the machine M and W, I can certainly do. Because I just say, is the string Q0 followed by W between the first two pound signs, which I certainly can do. What else has to be true of these configurations? CM has to be accepting, which means among the CM characters, what must appear there? Yeah, the accept state of M. So check if CM is accepting. Which also I can certainly do. Now, what do I do? What do I need to check about the other configurations? Right, so now I just need to check, for all values of I, does CI yield CI plus 1? Could I check that? Yeah, well, what must happen? Right around where the tape head was, there could be some differences because I can move left or right or change characters. But what about the rest of it? It's exactly the same. So there's only a finite number of things I need to check. Yeah.
For step 2, does it have to be C sub M or is it any of them?
It must be the last one because there's no transition once we enter the accept state.
I was thinking of like some tape and it could.
No.
I got it.
But you're right. If there was an accept that appeared before, that's not a valid computation history.
Okay.
Because I must stop at that one. Yep. And then now we just need to check if CI yields CI plus 1 for all values of I between 0 and M minus 1. And we just outlined how to do each one of those three things. So an LBA, we just figured out, can detect whether a given string, given a Turing machine and input, is a valid computation history. So maybe what we can think of is have an LBA either be that particular accepting computation history or nothing if there's no accepting computation history. Then use a supposed decider for eLBA to detect which one of those two outcomes happen. Okay? So to decide ATM, so on input M and W, build an LBA, let's call it B, using M and W as described above. So remember when I asked you, could an LBA figure out whether a given string is a valid accepting computation history? We said given a Turing machine and input W. Well, once this supposed decider for ATM starts up, I have the M and W right there. So I just build the LBA based on those two things. Well, let's see. We're going to have this LBA accept the accepting computation history if there is one, and reject everything else if it doesn't have an accepting computation history. So, well, if this LBA's language is non-empty, then there must be an accepting computation history of M on W. So what should my answer be to the decider for ATM? It would be accept, because M must accept W because there's a valid computation history. If this LBA's language is empty, could there be an accepting computation history? No. So what should I say for my decider for ATM? Reject, because M does not accept W. Okay. So run the supposed decider for E LBA, let's call it E, on the description of B. Then if E accepts, well, if E accepts, that must mean B's language is empty, which means it has, M must have no accepting computation history on W. So M must not accept W, which means I should reject here. Then the other case, if E rejects, then we can see that it's going to be accept. Because if it rejects, then it has some string. Well, the string better be the accepting computation history. Okay? So just by looking at the property of what an LBA could recognize, we can answer some question about given an arbitrary LBA. And then we can say the fact of trying to decide whether it has empty language or not is undecidable in general. Okay? Any questions about that?
In this case, ELBA was the decider for ATM, and since we said that we can build ELBA.
I'm supposing I can make ELBA.
Right.
Then using that assumption, then I can make a machine ATM decider.
And since we know ATM is
Yeah.
decidable.
Yeah, so since ATM is undecidable, ELBA is as well. Yep. So we just had this LBA had two outcomes, either be empty or the accepting computation history. Why does this not prove that ECFG is undecidable? Well, we can't decide, given an input, whether it has a valid accepting computation history or not, because that language happens to be non-context free, unfortunately. Okay? Other questions? So we're going to take a little bit of a third detour. I promised you that we'll revisit the questions about all CFG, which is determining whether an arbitrary CFG accepts everything, as well as EQ CFG, depending on trying to decide whether two CFGs have the same language. So let's start off with all CFG, and I'll let you think about EQ CFG. So this is just given an arbitrary CFG, and deciding or trying to decide whether or not it has every string in this language. And if you start trying to think, how would you decide that? Well, certainly the method of trying the empty string, then strings of length 1, strings of length 2, that's not going to work in general. Because even if it did accept everything, that method would run forever. And so you may think, well, there might be some other method that we could try, but what do you think the answer is? Well, we can't apply Rice's theorem because it's with context-free grammars and not Turing machines.
Got it.
If it was all TM, certainly I could, but it's CFG, so we have to resort to a different method. Rice's theorem for CFGs, no. This ends up being undecidable. Because I actually reordered the thoughts I was going to say. This is kind of sad because you can actually use all CFG to also show that EQ CFG is undecidable, which is kind of sad. Because it might be really useful to determine if two arbitrary CFGs have the same language, but turns out we can't.
It's sad because we can't say that.
It's sad because it would be really useful to determine if two arbitrary grammars have the same language. Yeah. Like if I made a change to the CFG for Python, for example, did I actually break the program or not, the compiler or not? That might be pretty important, but in general, that's undecidable. So how would we prove that all CFG is undecidable? Well, it turns out there are many methods of proving this, by the way, but one method is to use accepting computation histories, but the other way. We'll build a CFG that accepts everything that is not an accepting computation history. If there is an accepting computation history, then its language is not everything. But if it doesn't have an accepting computation history, then it is everything.
How is it everything?
We'll try to have the CFG that we build accept anything that isn't a valid accepting computation history. So we're thinking about it the other way here, and we'll see how to do that in a second. So like for example, if the start configuration is not a valid start configuration, then we accept that string because it's not a valid computation history. Yeah, so if there is, so I'll reiterate, if there is an accepting computation history of M on W, then the CFG we're going to build is not every string. Okay, it's not every string. But so if it doesn't have an accepting computation history, then every string will be accepted by this CFG, and therefore it will have every single string in its language. Okay, so it's just thinking about it the other way around. So instead of trying to either have empty or one string, we're either going to have every string or everything but one string. Okay? So this proof is pretty cool. It's kind of what we just did for LBAs, but the other way. So a question, given M and W, how can a CFG recognize all strings that are not accepting, so I'm going to abbreviate it because I hate writing it. So accepting computation histories of M on W.
Basically, just all computation histories.
Yeah, so it's all, well, because we can't apply the method we did before because of where we accepted only the things that are ACHs, because CFGs are not closed into complement, or CFLs are not closed into complement, which is the method that we would be trying here. So we can't do that in general. So we need to progress this roundabout way. Yeah, question?
Is M still a TN?
Yes, yes, yeah. So I should say thank you. Yeah, M is still a Turing machine. Yeah, so we're gonna still be doing a reduction from ATM in the same way. But we're having a CFG just recognize strings based off of M. Okay, well, what are some really easy ways I can determine if this string is not a valid accepting computation history? Yeah, the start configuration is not a valid start configuration. Okay? So C0 is not a valid config. Well, what is that? That's just sigma star. Sorry, not sigma star, gamma star. Those things that can appear on the tape. But it's just gamma star without the Q0, W1 through Wn. So if we take away the set Q0, W1, W2 up to Wn, we don't want that there. It's not quite this. There's a little more to do, but this is the idea. Well, let's see. Every single string, take away one string. Is that regular or context-free or whatever? What is it? Every string, take away one string.
It's reverse concatenation, right?
Deletion.
Well, let's see. If we phrase it another way, this is just intersection with the complement of this guy. Well, what can I say about that? Well, this first guy is regular, and what can I say about that guy? It's also regular. So this is regular. Oh, could a CFG recognize this then? Yeah, easy. Fine. What is another way I can detect that it's not a valid ACH? Yeah, the accepting one is not an accepting one. So CM is not an accepting config. Well, what can I say about this one? Is that regular, context-free, whatever?
It doesn't have the Q accept.
Yeah, well, I think along the same lines, we can just say that this is also regular, okay? There are some details to check, but the idea is here. It's almost exactly the same as the last one. Every single configuration that doesn't have a Q accept anywhere. And you can make this more formal, but I'm going to keep it informal. Well, what is another way that it's not a valid ACH? Yeah, between any two configurations, one does not yield the other. Do I need that many of them don't yield the next one, or do I just need one pair that doesn't work? Yeah, just one pair. But there actually is going to be a problem in a second. Well, what we are going to have here is CI. Let's suppose CI does not yield CI plus 1. So on the input, it's going to look like this. And I have to determine if there's not a valid transition between CI and CI plus 1. Could I do that with a CFG? What if they were exactly the same? This is not an actual valid proof, but what if they were the same?
They would still have to.
Could a CFG recognize the language W$W? No, because that's not context-free. We came all this way and we get blindsided by this. Is there a small variant I can do on this to make it so that a CFG could recognize it? Exactly. What if I instead reverse this guy like that? That is context-free. So if I haven't given enough definitions yet, a reversed accepting computation history is of the form. So C1 starts out normal, C2 is reversed, C3 is back to normal, C4 is reversed, and then keep going. And then let's just say, for sake of argument, CM is not reversed.
It's probably stupid. What about C0? Is it supposed to say
Yeah, thank you. I should keep the same notation. So let's say C1, I did it again. C1, C2, C3, and CM. Yep, thanks. Yeah, it should be identical.
So all odd computation histories are reversed?
No, I'm not. So this could end on a, like in this case, M would happen to be even, but I could be odd and end the last one reversed.
Oh, okay.
Yeah. So it's not saying anything about the length of the computation. Well, could I recognize whether an arbitrary pair, like say C2 and C3, is not a valid transition between C2 and C3? Well, let's see. Let's look at what the configurations look like. So I'm going to blow it up a little bit. There's stuff on either side, but let's say that this is C2 and this is C3 reversed. Okay? Well, is there anything I can say about characters around any particular place because the C3 is reversed? Well, whatever character was right here, where is it on the C3 reversed part? Yeah, at the beginning now. So it's going to be right here. And let's say the next one's right here, whatever character it is. Where's that second character? It's right here. So right at the beginning, for a while at least, they're exactly the same. Ignore the transition part for a second. What about after the transition part? Anything involving the transition? What must happen after? They're the same again. So we only need to handle one place where they're different, possibly. So the way you can handle that particular case where the transition, let's say, happens here and here, the way you handle that is there are only a finite number of possible transitions that could be applied right there. Then just make a rule for each. Okay? So you just make a rule for each of the possibilities that can't happen. And then afterward, you'll progress to a variable which just checks if the characters afterward are the same. So you start off having the same characters, then you just check the finite number of possibilities that aren't valid transitions, and then afterward, they must be the same. Okay? What language is this, where you have a computation here, #, reversed computation? Well, it's kind of like palindromes. Is it regular, context-free, or what? It's not regular. Is it context-free? Yeah, it's context-free. So this is a CFL. Oh, it could be in the first case, or the second case, or the third case, right? What is a regular language, union a regular language, union a context-free language? A context-free language. So can I build a CFG for it? Heck yeah. So regular, union, a CFL gives us a CFL. So therefore we can say a CFG can recognize all strings that are not ACHs. I get chills too. All right. It is a pretty cool proof because it's exploiting the structure of the accepting computation histories, but we had to make a slight modification, but that's easily done by a context-free grammar. So to decide ATM, so let's say on input, just to formalize it, M and W, build a CFG, let's call it G, as above. And of course, this is based on M and W. Okay. Cool.
And
The-
that's not the encoding of M and W, but just M.
Yeah. The encoding is only when we need to feed a string to places. We just drop it because we don't need the string. Yeah.
What does A and ACH mean?
Accepting computation history. Yeah. I didn't want to write it all over. Build a CFG as above. Run the supposed decider D for all CFG on this grammar that we just made. Well, let's see. G is going to have it's going to have two possibilities. Either every string in its language or every string minus one string. Because there can only be one accepting computation history. Well, let's see. Since D is a decider, supposedly, it either accepts or rejects. Okay? It either accepts or rejects. Well, let's see. If D accepts, that must mean that G accepts every single string. So could there be an accepting computation history? Well, we just made the G that we just built. It accepts everything that is not a valid ACH. But D just said it accepted every single string. So could it have had an accepting computation history? No, it couldn't have. So what should I say for my decider for ATM? We're trying to decide ATM. And we just determined there is no accepting computation history. So could have M accepted W? No. So what should I say here? Reject. Okay? If D rejects, that must mean it doesn't accept every string. But the only possibility is that it accepts every string minus one, which is the accepting computation history. Oh, what did that mean for M on W? It must have accepted W because there is an accepting computation history of M on W. Okay, so what should I say for my decider for ATM? Accept. Okay, so the idea here is that since we couldn't use the idea before and then just complement the language because CFLs are not closed into complement, we had to work the other way in accepting everything that is not an accepting computation history. We were able to show that that language is recognized by a context-free grammar. We can make one for it. And by doing that, if there was a decider for all CFG, then we can determine whether or not M has an accepting computation history or not. Okay? Any questions on that? So right at this second right here, that's the material that will be on non-bonus problems. So everything from here on out will only be for a possible bonus problem. Okay? Any questions otherwise?
Can you make that announcement again, what you did at the earlier? Or no?
I mean, I could, but we could move on. I have some really cool things if we want to move on to some things that I know we're more interested in. Not game theory, but along that line.
Shows cool stuff.
What's there?
Shows cool stuff.
Yeah, shows cool stuff. All right.
Show us the program that you got running for.
I'll show you on Monday. The last Monday. Yeah, I'll definitely show you. All right. So what have we done this entire class? We've talked about a lot of things. We talked about, we started off with DFAs and NFAs, this really simple model for regular languages. And I mentioned then that even like in the product construction, we can make really massive DFAs, but we don't necessarily care because as long as there is some DFA that recognizes that language, we don't care. Then we moved on to context-free grammars and PDAs. Again, same answer. Turing machines, same answer. Like in the case of converting a non-deterministic Turing machine into a deterministic one, that takes a massive amount of time, but it's still finite, so we don't actually care. But you all and I know we live in the real world. We don't have until the heat death of the universe to figure out whether my particular Turing machine accepts an input. So if we can talk about, let's say, Turing machines that have some particular property, maybe they don't run too long, or if you're interested in big data, they don't use a lot of space or whatever, or don't move left too many times. Anything that we can come up with that's a restricted model, maybe that can be more realistic to what we want to talk about. So here's a question. So here's the end, here's where we're going to start chapter 7. And I'm skipping a little bit of the beginning of chapter 7, which I assume you already know, like big O notation, that sort of thing. So here's a question. What types of resources do we want to restrict?
Time and space.
Yeah, time and space for sure, right? So definitely time. We don't want our programs or Turing machines or whatever to run for too long. And space. Maybe I have all the time in the world, but I have a really small amount of space, maybe on an embedded platform or something. I don't want to have too much space, but I can run for as long as I want. Maybe we can talk about that. Maybe we can talk about space and time bound, where I restrict both of them at the same time. And that actually turns out to be really interesting too. Okay? And of course, the list goes on and on and on and on and on and on. But the ones that we're going to talk about, at least for what we're going to get to in this class, we're going to only talk about time. But if you're really interested about the space part, you can talk about, you can look at chapter 8 and I think 9 in the book as well. But we're going to stick to chapter 7 for now. Okay, well, how do you even talk about having a Turing machine run for some amount of time, right? How do you talk about that? Well, maybe we can talk about something related to, say, big O notation. Like if I have this program that runs in O of n squared time, let's say, then what does that fundamentally mean? That means no matter what input that I'm given, it runs in at most some constant absolute constant, times n squared operations. What is n here? The size of the input, right? It's not some abstract thing that maybe some of your other instructors have taught you about. N precisely always means the size of the input, always. Okay? So you can actually get into some logical fallacies about some algorithms running in polynomial time, for instance, but actually take much longer because of how the input is presented. So it precisely means the number of, say, bits or whatever in the input, the size of the input. Okay? So we're going to define time in capital letters of f of n to be the set of all languages decided by TMs that run in O of f of n time for all inputs of size n. Okay, so all this means is that I'm going to be talking about all the problems, if you want to think about it that way, all the problems I can solve in constant times f of n time. Okay? So let's do one example for now. So this is, let's say, 0 to the n, 1 to the n, where n's at least 0. Can I decide this in linear time? No. If I could, then there's a DFA for it. But this language is not regular. So I need at least O of big omega, no. Yeah, big omega of n time at least. So let's see. What is a simple algorithm that I could decide this with? Well, the one we talked about where you mark 1, 0, then mark 1, 1, go back, go back, go back, go back, go back. How long does that take? A constant times how long? N squared. Because I'm moving roughly, let's say, the number of the length of the input every single time I mark something. Well, length of input roughly times length of input roughly, that's about n squared if the input's length is n. Okay? So this belongs to time of n squared because I can decide it in constant times n squared time. Okay? Okay, so I won't prove this here, but all, not capitals, all CFLs, there's a famous algorithm by Cook, Yosami, and I forget one other person. I believe it's in chapter 2. It's a dynamic programming algorithm to decide whether a given context-free grammar accepts an input in cubic time. So all CFLs are in time of n cubed. It's a very cool algorithm, but lack of time. I won't prove it. Okay? Cool. So let's extend this a little bit to non-deterministic machines. So we're going to define n time of f of n very analogously. So it's the set of all languages decided by non-deterministic Turing machines that run in f of n time for all inputs of size n. there's a little bit of an issue that we'll address in a second. But it very well extends to non-deterministic machines. Okay? What's the issue here? Well, depending on the non-deterministic choices, maybe one particular computation path takes an extremely long time, whereas all the others take only a little bit of time, right? That's certainly possible. Or maybe one computation path ends really quickly and all others run forever, possibly. How do we reason about that? So we say an NTM runs in time, let's put the constant in, O of f of n, O of f of n, if all computations take at most O of f of n transitions. So here I'm guaranteeing that the height of how far I do computations is at most the guaranteed time bound. So here I'm just guaranteeing no matter what you do, you will run in at most O of f of n time. Okay? So probably the moment you've all been waiting for this entire class. Ready for it? We're going to define P to be the union over all k at least 0 of time n to the k, and NP to be same thing, not 3, of n time n to the k. These two definitions are probably the most misunderstood thing in computer science. They have a very precise definition. We said that every Turing machine runs in at most f of n time, and we define P and NP to be any constant you pick and union all the times of n to that particular constant. Okay, it has a very precise definition. Okay, and the major conjecture, which is unsolved, is P is not equal to NP. This is a conjecture. I could say that I'm going to prove it, but I will be leading you down the wrong path. No one knows for sure whether or not P is equal to NP for many, many reasons. So I may get into a few of them, but one technique is called using oracles, and you don't have to write this down. So the idea is if you had like instant access or instant answering of some really, really tough problem or any problem you like, could you separate P versus NP? And it turns out there are some problems where there are equal relative to this supposed all-know-it power. And you may think I'm completely bonkers right now, but if you are interested, look at chapter 9. And there are some languages for which they are different. So we can't separate them.
Meaning that they're different, meaning one can be greater than the other, and that would be for that same.
Well, I know that P is a subset of NP because time of n to the k is always a subset of n times n to the k. But I don't know whether they're different or not, unfortunately. There are many other techniques and many failed proofs using function theory, algebra, many, many techniques. No one has ever separated them. And I doubt that it'll be proved within the next century, unfortunately. But that's what pretty much every single computer scientist in the world thinks right now. And we'll get into that very shortly.
So what kind of insights, do you think it needs to be? a lot of this stuff happens in like baby steps, right?
Yeah.
So what kind of baby steps would it take to get to a point where
So I have a great, I guess I can talk about in 5 minutes. So some of you may be interested, if you're in the more hardware side, in circuits. So maybe you may want to think, okay, I have these N input pins that can be either turned on or off, and this output exactly one pin. And your goal is to figure out, using this black box circuit, whether or not there is an assignment to zeros or ones on each of the input pins to turn the output pin on. And that problem turns out to be NP complete. And that's a problem that we believe, if this is true, this conjecture is true, that is not polynomial time solvable. There's no efficient algorithm for it. And ways to separate P versus NP, if you want to look at chapter 10, are what are called circuit lower bounds. And so the idea here is that you try to prove what is the lower bound on a circuit to what is called a circuit family, to try to decide whether or not you can actually do this. And you definitely need at least N here, but for circuit lower bounds, if you can prove a super polynomial lower bound, so at least a polynomial lower bound, then you've separated P and NP. But the best we've done, and I think this is like 2 years ago or 1 year ago, is 5n plus little o1 is the best lower bound for circuit sat. Sorry, that problem is called circuit sat, satisfiability. But so we've only, within a few decades, have raised this bar from n to roughly 5n plus a little bit. So extending this to super polynomial is incredibly far away from this. And we'll actually define NP completeness probably next class. And what you'll see is that if we can show that one NP complete problem is in P, then you've showed that P is equal to NP. But that is certainly very hard to do, and no one's ever done it yet. There's some techniques along what is called parameterized complexity. So this whole area is called complexity theory. There's an area called parameterized complexity theory, which is pretty interesting and hot right now, which is you try to separate out what the hard part of a particular problem is. And then if you can show that in that model, there's a nice theorem that says the analog of P and NP in that model, if you can show that they're different, then you can show P and NP are different. There's different techniques in what is called geometric complexity theory. So I know I'm boring you to tears now, but it's super cool. So geometric complexity theory is analog of P and NP, but in terms of polynomials over the real numbers and the complex numbers. And then you can have the analog based on whether or not you can find roots of these polynomials. And if you can separate those, then you can separate P and NP, but no one's done that yet. So, and there are hundreds of other avenues. So I'll share with you 2 quotes and I'll let you go. So there was this, my advisor was in a class with Steve Cook, who was one of the pioneers of NP completeness on this stuff, and my advisor asked him, so what if we were able to prove P is not equal to NP? Well, he said, when this class is over, then a limousine will appear on the front. You'll be hoisted in that limousine to a full tenured professorship at Stanford where you'll never work for the rest of your life. So it's a famous open problem, one of what is called the Millennium Prize problems. And if you solve it, you'll get $1 million, but that's the least of what you'll be able to have at that point. Another, what was the other quote? Oh, no, I can't think of it.
you heard about the thing where assuming human, right? Problem solving?
Oh, yeah. Well, I'm trash.
Oh, yeah. So there's a famous quote that if you start a theoretical computer science lab, with the goal of trying to prove P is not equal to NP or anything similar to that, you'll instantly lose funding. Because this question has been tried and tried over and over again, and it seems hopeless at this point. That's actually funny. But believe it or not, if you search P versus NP page, there are some hypotheses that say that the question of P versus NP escapes what is known as classical set theory. And it actually is undecidable to show whether, or unprovable whether P is equal to NP or not. So that's actually, can be a valid hypothesis. But some people believe that it escapes what is called ZFC, which is the standard set theory today. So all that and really cool stuff starting Monday, but any questions otherwise?
What's your personal hypothesis?
In terms of? Oh, it's definitely not true, but I can't prove it. It's almost certainly true, yeah. Other questions? All right, I'll see you Monday.